The next idea that we need to discuss, these are some important things from the exam point of view, that's why I am discussing. Otherwise, we are not interested in these things right now. So, we are done from the point of view of the sequences, series and so on. The next idea should be the limits and continuity. I am not going to define, okay, what is the limit in rigorous sense and how to define the limit, how to find out the limits and when a function is continuous. Now, we are moving out of sequences. We will not be having any word like a sequence, like a series from now onwards. We have three things to discuss now. What is a function, and what is the limit of a function, what is continuity of a function. We are not discussing what is a function because that's very elementary. What is limit? But we will define, okay, what is continuity. And why we will define it? Because of some reasons. Then after that we will come to, okay, what is differentiability. But we will not discuss, okay, what is differentiability, how to define it. We know very well there is a certain limit. If it exists, the function is differentiable, otherwise it is not. We will not discuss that. Then we will directly move towards integration. Okay, what is Riemann integral? What are the conditions for the Riemann integral to exist and so on. So we will be discussing one thing is continuity. Then we will directly move towards integration. Okay, so everyone knows what is the definition of a continuous function at some point. We know very well at that point the limit of the function exists. Limit of function exists means the left hand limit exists, the right hand limit exists, and they must be same. And the value of the function at that point should be same as the limit. That's the definition. But that's not the rigorous one. We are going to put what we call the epsilon delta definition for the continuous functions. And that is important, that's why I am going to put here. What we are going to do now, we'll define what do we mean by continuity, then what do we mean by the uniform continuity. This was uniform convergence. It has no relationship with the uniform continuity because uniform convergence comes in the sense of sequences. We don't have sequences, we have only functions. When a function is continuous, when a function is uniform continuous, and third thing is when a function is Lipschitz continuous. We have to discuss these 3 to 4 things for now. These are very much important for the exam point of view. And these are the things which are maybe not explained anywhere, and these are being asked in the exams. This is the problem. Okay, continuity is very weaker notion, we know very well. We have to make it a bit strong, then we go towards what we call uniform continuity and Lipschitz continuity. So, simply, what is continuity of f that let's say runs from I to R? How to define this? So we say that f from I to R is continuous on, let's say, some x naught in your interval, because we are defining the continuity at a point. Then we say that, okay, if a function is continuous at all the points in the interval, then the function is continuous on that whole interval. Okay, how to define this using what we call the epsilon delta definition.
Limit minus delta.
So we are saying that we have a function f of x minus f of x naught, because we are taking the continuity at x naught. This should be made as small as possible, less than epsilon. When it means for all epsilon, you choose any epsilon, this thing must happen. But there are some extra conditions. There are some extra conditions that we have to put so far. There is nothing else. This difference between the value of function and f of x naught should be made as small as possible, but when? when you choose any epsilon corresponding to this, there exists some delta. Whenever x minus x naught is made smaller than delta, it implies that this thing should be smaller than epsilon. It means this is the main condition, but this will work for all epsilon, whatever epsilon you choose, or whatever epsilon you give me, this must hold. This must hold whenever this happens. So this is the condition, what we say the function is uniform continuous, continuous. But when this happens for
all, what you say?
for all x.
What you would
Yes.
particular to what x not only is for all.
For all x. This thing must work for all x. Okay, what does it mean basically? It means that if the difference in the arguments or inputs is small, it implies that the difference in the outputs is small. So small difference in the inputs implies a small difference in the outputs. So we call this thing to be a continuous function at x naught. For example, we have a function, let's say, and we want to check its continuity at some fixed x naught. Then you take some boundary of this x naught, let's say this is a boundary. We call this thing is this, because we can write this thing as x minus x naught is between delta and minus delta, and we can write that this thing is x naught plus delta and x naught minus delta. We call this, I think, delta neighborhood of x naught, or a ball, an open ball of radius delta around x naught. We call it an open ball. So whenever we restrict this thing in this domain, what exists that the value of the function, which is f of x naught, should be between these two values. Means this is the limit. This is what we call f of x naught plus epsilon, and this is what we call f of x naught minus epsilon. So whenever you have some open ball around x naught, there must be some open ball around f of x naught. And the open ball around x naught have radius delta, and open ball around f of x naught have radius epsilon. So that's the thing. That is how we define the continuity. So from the point of view of definition, we are clear, okay, what happens. Okay, the next thing is go ahead with what we call the uniform continuity. But before this, let me give an example. F of x is 1 over x, and you know very well it is not continuous at x is equal to 0. But my domain is from, let's say, not 0 towards infinity. This is that. So this is that. You know very well on this particular domain, it is continuous. It is continuous. But the problem is that in this domain it is not uniform continuous. So we have to basically discuss and define what do we mean by uniform continuity. What is the problem? That when you draw the graph of this function, that looks like somehow like this. It looks like this. This is 1 over x from 0 to infinity. It is continuous in this domain. Now, if I want to define the continuity at x naught, what will I do? I will make some I will choose some domain, and you know very well this is going to be the epsilon neighborhood, and this is going to be the delta neighborhood. This is the case. Now, what is the problem in this one exactly? The problem is around x naught you have some ball of radius delta, and around f of x naught you have some ball of radius epsilon. Now when you take this x naught at this point, then what happens? I am taking now my x naught here, and I am taking some interval, then you see what happens. Then my this delta becomes very much small.
Epsilon changes.
And if I am keeping my epsilon same, then this delta becomes small. I am keeping my epsilon same. This is 2 epsilon because epsilon becomes 2 epsilon. Then my delta becomes very, very small when I go near to 0. This is the problem. What we say, okay, for all epsilon, there must be delta such that this happens. So for all epsilon means you choose any epsilon. But corresponding to that epsilon, the value of the delta changes very much. When you go near to 0, the value of the delta becomes very, very, very small. This is the problem. This is the problem, that when you go near to 0, this function is continuous, but we call this thing is not uniform continuous, because there is a problem in choosing epsilon and delta. Your epsilon might not work for every point, and your chosen epsilon should work for everything. If it works for everything, we call it is uniform continuous. If it does not work, we call that it is continuous, but not uniform continuous. So uniform continuity is stronger condition as compared to continuity. So continuity is not uniform continuity whenever we are approaching some value, and along that value the value of your function changes at a greater rate. You can see whenever we go near to 0, this function explodes to infinity very fast. We are not saying okay 0 is included in our limit, but whenever you go near to 0, the value of your function changes at a greater rate. This is what we call the simpler notion of uniform continuity. Sir?
What I have understood, sir, there is a doubt in my mind. As far as you are saying that the distance between the two input points, okay, it's quite different as compared to the difference between the two functions what we are taking outside. So what I understood, we have mean with the delta and epsilon, we have not mean what the change is there. The delta becomes equal for every two input points. So do you think that it's a uniform continuous or not?
No, the basic thing is that you choose an epsilon for all epsilon, and you corresponding to that epsilon you choose a delta. Okay, but whenever you change your value from this x naught to that x naught, then your chosen epsilon and delta will not work. Okay, you choose some epsilon, whatever, then this should work, let's say for all x. But unfortunately, your chosen epsilon does not work for all x. When you go near to 0, the epsilon that you have chosen so far will not work for this, but it works for this. So we say that whenever you go near to 0, your function is not uniform continuous. Thus, the case is same. The case is same as we discussed what we call the uniform convergence and pointwise convergence. But the problem is this one, that you choose an epsilon, that epsilon must work for all x. But unfortunately, whatever you have chosen does not work for all. This epsilon works for this, but this epsilon does not work for that when you go near to 0. That's the problem basically. But if you don't go for the definition, at least we can understand okay what happens as you go near to 0, the rate of this function increases or decreases or whatever. It means the difference between the argument becomes very, very large. When I take this value, maybe I am going to very much near to infinity, and if I am taking this value, there is a smaller difference, but this would be something like 1000, and when I take this value, this would be in millions and billions and trillions, so the difference becomes very much large. That's the problem. So on this interval, this function is continuous but not uniform continuous. this function is uniform continuous in this interval. Do you agree? Interval is very much important. This function is uniform continuous on this one, but not uniform continuous on this one.
Sir, closed interval होने asymptotes आते होते नहीं जाते?
Yes, asymptotes and the greater change in the value of the function.
सही बात है समरी मुझे जो समझ में आता अगर ये जो मॉड ऐसा चेक करना हो एप्सिलॉन अच्छा था हर मिड पॉइंट के दरमियान
Yes.
जो को मुझे रिजल्ट मिले तो
Yes.
और फिक्स कैलकुलेशन एप्सिलॉन थे वो ताज मतलब वो सेम अथवा जो थ्रूआउट
Yes, throughout same नहीं. It's not same throughout. That's the problem.
वो रहे तो डेल्टा चेंज ही नहीं रही
Yes.
डेल्टा भी हर जगह वेरी करती
Yes. Delta vary the color, so it is a definition of continuity. That's okay.
ठीक है
But the problem is uniform continuity is different. You can understand in the sense of greater change.
अच्छा इन्हें मतलब अगर यूनिफॉर्म कंटिन्यूटी चेक करनी चाहिए तो हर पॉइंट में ट्रेच आर पॉइंट भी पुट के लिए
Yes.
अगर एप्सिलॉन वेरी थी करे
Yes.
तब कुछ अगर यूनिफॉर्म कंडीशन
Yes. That's
in case of the subject के साथ intervals दिनला ये lower limit है upper limit के लिए साथ चाहिए क्या तो ते behavior चाहिए function जो
yes. How? Yeah, the behavior. Behavior is something very good. Because what I understood from this one, if we want to check the functions to be uniform continuous, we should check their asymptotes as well. Because near to 0, this function has an asymptote. But if I am taking interval from 1 to infinity, it means I am starting from 1. So then this function is continuous as well as uniform continuous. Continuous as well as uniform continuous. Okay, so what is the next idea? What about this function?
It's a parallel.
And let's say this interval minus infinity to infinity. Is it uniform continuous or not?
So asymptotes
It should be, but according to the definition it is not. Because when you go near to infinity, what happens?
So rapid change ना
Yes.
zero नहीं दो
When you go near to infinity, there are greater changes in the value of this function. For example, you take x to be something very, very large, like 10 power 23. And you take x to be 10 power 23 plus 1. And you take their square. These two values will differ a lot. So when you increase your inputs towards positive infinity, the difference between the output becomes very, very large. We can say that there is an asymptote of this function near to infinity. There is an asymptote near to infinity. It does not make sense, but there is an asymptote near to positive infinity and near to negative infinity. So we can see there are lots of examples to check that whether a function is uniform continuous or not. Do you have some examples?
It's a uniform continuous.
no sir
It is not uniform continuous. But if you restrict your domain, okay, if you say that okay minus 1 to 1,
Yeah,
then it's uniform continuous. But from minus infinity to infinity, it is not uniform continuous. How about this?
again the near to infinity ना सकते approximately
Now, तमाम small चीजें value वाले हैं
Very small.
small चीजें नहीं दो
Because this goes like this. So this is uniform continuous from 0 to infinity. This is uniform continuous because the changes in the output becomes very big.
horizontal asymptotes हो जी
Yes. So and what about this sin x? So it is uniform continuous. This is uniform continuous as well from minus infinity to infinity because the changes in the outputs are very small. It is a bounded function, we know very well. And how about this?
You ना इन्हें asymptotes होगा
No, we are going to say that okay x belongs to 0 to pi by 2.
why
अच्छा
Still near to pi by 2 there is an asymptote. The values change rapidly. So it is continuous in this interval,
It's kind of uniform,
but not uniform.
not uniform.
Not uniform
It's
continuous.
not uniform.
Not uniform continuous. So don't mix the notion of uniform continuity with the continuity
Yes, right.
when you are appearing in the exams. Otherwise, puro blame mana botte indu. So So 1 upon x, there are some key examples as well. Not uniformly continuous on 0 to 1. You can see this thing, we have already discussed. Near to 0, there is a problem in this function. So x square, not uniformly continuous on, let's say 0 to infinity, because near to infinity there is a problem. This function changes rapidly. This is uniformly continuous on 1 to infinity because we are not going near to 0. And number 4, x square is uniformly continuous on, let's say, 1 to 2. So it depends upon what are your inputs and what are your outputs. We had this question in our test as well.
So,
Yes. They gave different functions and they asked, okay, which one is uniformly continuous
a
and which
key,
one is not.
so a key idea, as my personal opinion, that if you see the interval of any function like you have given that either from one side or both sides, if it is closed, so this will become uniform continuous. Is it?
It's a theorem.
It's a theorem.
It's a theorem. We are looking at that theorem as well. So we have to do 1 or 2 things related to this one as well. So there is a theorem, let me write it. Again, if I write the definition of continuity and uniform continuity, we have seen the change of quantifiers, the change of the order of the quantifiers. If I say continuous means you have to check for all x naught, that thing happens. And uniform continuity means for all epsilon. And that epsilon that you have chosen must work for all x. In continuity, we are choosing x, but okay, our function is continuous at this x. Okay, so that's the difference between the order of the quantifiers. So there is a theorem, let me write, there is something very much important.
Yes, what is doing also? Uniform continuous.
Yes, if there is an interval from A to B is closed and bounded. Closed and bounded interval. And we know very well an interval that is closed and bounded is what we call the compact.
A is interval, sir.
A is an interval which is closed and bounded. We call this is compact set. Okay, and a function that runs from A to R is continuous. The function must be continuous on A. Then f is uniformly continuous on A. Then f is uniformly continuous. Are you agree with this? So yes. But if I take this thing from 0, 1 to R and my f of x is 1 over x, this is not uniformly continuous because this is not closed and bounded. But if I do this, again it is not uniformly continuous. The problem is it does not satisfy all the conditions of the theorem.
Undefined with the
Yes, that's the problem. this function must be continuous on this whole domain, but if you include 0, this function becomes discontinuous. If you exclude 0, then we are not satisfying the first condition. Yes, that's a problem. That's a problem. So this is what we call the theorem that relates the compact sets with the uniform continuity. Yes, means compact. Compact. There are 3 definitions of compact set, but we have defined compact sets in these ways. We have defined the sequentially compact sets earlier in our previous lecture. So the next concept is what we call the Lipschitz continuity.
Pronunciation tough.
It's not tough. It is very much important when we discuss differential equations, because in the existence theorems we need Lipschitz continuity. So a function is said to be, so f is said to be, let's say, Lipschitz continuous if what happens? Lipschitz continuous on A if there exists some L greater than 0 such that for all x in A and y in A, it means I am taking 2 points, not a single point. What happens that f of x minus f of y can be bounded by L times x minus y. This is what we call the Lipschitz continuity.
So your limit multiply x minus y in integral.
No.
Times are
F of x minus f of x y
less than.
should be bounded by L times x minus y.
This means that we input on the point.
Yes.
Yes. Times limit में रखेला ना.
Yes. If you take L is equal to 1, then what happens? Okay. The difference in the outputs should be smaller than difference in the inputs. Difference in the outputs should be smaller than difference in the inputs. This is the idea. Okay, now the main idea is, this is the definition of Lipschitz continuity, and this is very strong notion as compared to continuity and uniform continuity. We know very well if a function is differentiable, it is continuous. We know very well.
Yes.
But the reverse is not true always. So let me give you a sketch that if a function is differentiable, it implies that it is Lipschitz continuous. Or simply if a function is differentiable, it is Lipschitz. Okay.
Inverse not true.
Inverse is not true always. If it is Lipschitz, it must be uniform continuous. This relation is very much different. We are coming to that later on. And if a function is uniform continuous, it means it is continuous. So from differentiability to continuity, I have added 2 extra things. Differentiability implies that it is Lipschitz. Lipschitz means Lipschitz continuous. Whenever you listen the word Lipschitz, a function is Lipschitz, means it is Lipschitz continuous. It means it is uniform continuous, and uniform continuity implies continuity, but the reverse order is not true always. And there is another thing that comes in between this, what we call a function to be Holder continuous. It means this thing should be less than L times some power of this thing. And when this power becomes exactly 1, we call it as Lipschitz. Otherwise, if the power is something else, we call it as
Holder.
it is going to be Holder continuous. But we are not interested in this thing right now because this thing comes in maybe advanced courses. But if the value of L becomes between 0 and 1, then we call this Lipschitz continuity to be contraction. Contraction means the value of the outputs is smaller than some portion of the value of inputs. This is the difference in the inputs. I am multiplying with L, and L is between 0 and 1. It means L makes this difference even smaller. You multiply with 0.1, 0.5, it becomes this one smaller, and your outputs are even smaller than that one. This is what we call the contraction. It is very much used in Picard's theorem on convergence, but we say, okay, in numerical analysis we have Picard's solution for the ordinary differential equations. We say that their solution converges regarding certain conditions, otherwise there is no any convergence like that.
Sir, जगह जो मानो जरूरत ना बड़ी कुछ हम था समझो जो वर्किंग लिपशिट यूनिफॉर्म आसान समझिया ये डेफिनेशन समझ में आया वो जो ग्राफिकली आप जैसे उनमें तो सेम होते एप्सिलॉन था तो जैसे इतने ए लगा खास को
it's very strong. Let us come to that. How? This thing says this thing. What is this?
Limit on definitivity.
What is this? Slope.
Secant line.
You fix your y or fix your x. I am fixing my y to be, let's say, x naught. Then what happens that I have a function at some point x naught. The slope of the secant line or whatever it is, the slope is just bounded by L. It means I am taking a line with the slope L, and what happens that within this interval, this is the point, the slope of this line is, let's say, L, and the slope of this line is minus L. In this neighborhood, if your function lies between these two lines, we call that is Lipschitz continuous, otherwise it is not Lipschitz continuous.
Then point in the slope same rather.
No, I mean to say, I have this line with the slope L. I have this line with the slope. Within some neighborhood of this one, your function must lie between these two lines. Within some interval, if it goes beyond this, that's a problem. That's a problem. Yes. So you fix your L. You can make this L smaller and smaller. If you make this smaller, these two lines will come nearer and nearer to each other. Then the difference between the f of x and f of y and this should be smaller than L. It means that your function must lie within this interval. If it does not lie, that's a problem. So this is very strong as compared to this. Okay, you say that within that interval your function should not increase so much, but it should be between that two lines. That's very strong notion. So mostly we take Lipschitz continuity. If we are satisfied with this, it means we are satisfied with uniform continuity as well as with the continuity. But differentiability is something very much strong.
Sorry, cross second. Hey, possible.
Differentiability is not a good thing because we have so many functions which are not that much good. So we always do these things. Okay, what do you mean by Lipschitz and uniform and simply continuous? Okay, so the next thing that we need to do, I think we are done up to here.